webinar is entitled The Science Behind Nanobubbles, How Nanobubbles Improve Agriculture Input Efficiency, Soil, and Plant Health. This is the second of our series of Science Behind Nanobubbles webinar series brought to you by Moleaer and Malvern Panalytical. Our presenters today are Warren Russell and Dr. Ragy Ragheb. Warren Russell is Moleaer's co-founder and chief commercial officer. He's an experienced entrepreneur with over 15 years of business management experience in the wastewater treatment and environmental services industries around the world. Prior to leading the commercial efforts for Moleaer, Warren, a graduate of the University of South Africa, founded Irrigation USA and Evodyne Technologies, which focused on environmental consulting and designing wastewater treatment processes for municipal, industrial oil, and gas applications. Our second speaker, Ragy Ragheb, is a technical specialist application scientist with Malvern Panalytical, specializing in a number of light scattering technologies and GPC-SEC product lines. Ragy received his PhD in macromolecular science and engineering from Virginia Polytechnic Institute and State University, and completed his postdoctoral work in biomedical engineering at Yale University. His research focused on the fabrication and characterization of various synthetic and metal-based nanoparticle systems for theranostic and drug delivery applications. So before we begin, I'd like to welcome you, our attendees, and explain some of the interactive features we'll be using today. Right now you see on the screen some FAQs, so if you're having any issues with audio or the visual, please follow these instructions. We also have a few interactive features. So you'll see a poll in the view. This is a private poll, and it's an easy way to indicate to us if you would like more information about any of the systems or technologies presented today. And you'll also see a survey up there. So before you leave, we'd really appreciate it if you could take the survey. It's how we improve our webinar program. Now, we would appreciate your questions, and they're welcomed and encouraged. In order to ask any questions, just use the Ask the Speaker area on the right side of your screen. Type your question in and send it. We'll have a Q&A session at the end. And you can also review submitted questions and vote on them, and this will help us prioritize the questions that we address in the Q&A session. Note, we are recording this web seminar, and it will be posted in our on-demand content area of our website, located under the Webinars and Events tab. If you're watching this on demand, you could send questions or comments to events@malvernpanalytical.com. Now I'm going to get our presenters on the line. Hello, Warren and Ragy.
Hey, Kathy.
Hi. So, Warren, would you mind giving us a summary of what we'll see today?
Yeah, very much so. Firstly, good morning, good afternoon, good evening, everybody. I appreciate everybody's participation today. So this is the second webinar, which is a follow-up from the fundamentals that we did with Malvern a few months ago. And this is essentially taking some of our observations and learnings over the last few years, keeping into mind that Moleaer really started our technology and commercialized it, focused on water treatment, but really it's the emphasis around treating irrigation water has become a pillar of our business. And over the last few years and hundreds of installations, we're going to share some of those tidbits of information, particularly in today's climate, which is so relevant, where you've got water scarcity, water quality issues, high input costs, and we're going to give you a little bit of our insights of how we think nanobubbles play a role in improving those efficiencies in today's growing climates.
Well, great. Sounds good. So, Warren, you're set to begin.
So I'll be going first, and Ragy will jump in a short bit. So first, let's talk a little bit about nanobubbles at a high level and its role and impact on irrigation water. So we've kind of broken the high-level attributes into these different groups, starting with surface tension reduction. So there's a lot of emphasis right now, particularly sort of commercially out there, in the role of oxygen, and it's quite often paired with nanobubbles, and certainly the role of oxygen is instrumental in improving plant health. But today's conversation is really going to be focused more to do with the nanobubbles and how nanobubbles influence and change the properties of water, and how that will be applied in agriculture and irrigation applications. So starting with surface tension, we're looking at how nanobubbles reduce surface tension and how that affects capillary action and how water penetrates through the soil column, the impact that those nanobubbles and capillary action can have on soil compaction and reducing soil compaction. And then also, most importantly as well, is sort of improving the mobility of sodium and certain salts in that soil as well from a leaching perspective. And then nutrient distribution. So nutrient efficiency, particularly as we know that the cost of nutrients has increased so significantly over the last at least 24 months, looking to look at how nanobubbles improve that distribution uniformity and efficiency of nutrient uptake. Then second to that, irrigation system hygiene is a good amount of information out there and research looking at the role of nanobubbles and how they improve biofilm removal and preventing scale as well in irrigation systems, and looking at this to, at very least, complement chemical treatments, in some cases possibly replace it. And then also soil microbiology, how these nanobubbles influence the soil microbiology, the way that they interact with nutrients, and improving things like nutrient conversion and mineralization and enzymatic action in the soil. And also, again, sort of kind of tying that all back to, once we improve these different foundation elements and improving the way that we apply and utilize inputs in the soil. So Moleaer's mission is really harnessing nanobubbles to improve the properties of water, and ultimately in ways that we can improve efficiency of a particular application. We've now, over the last, I think, 6 years, just crossed over about 2,200 installations and 51 in different countries, working in a fairly wide variety of applications, from wastewater to mining, oil and gas, aquaculture and irrigation. There's a lot of commonality in the way that we approach these different processes by applying the nanobubbles, and particularly there's when you look at the correlation between the objectives in mining and what we're trying to do in soil, we can borrow from these different learnings, and that's some of what we can share today. And as you can see, it's a pretty broad spectrum of climate, soil type, cultivation method, you name it. We've covered a pretty broad spectrum. So some of these are some key takeaways from that, and obviously there's a lot of density that we can go into, but I'm going to just try and keep it at a high level today, and we'll cover that. And then any subsequent questions, please, by all means, we can go into more detail down the line. So for some of you, hopefully this is not too repetitive from the last fundamentals. Those that are new and not familiar with nanobubbles, at a very, very high level, there's lots of different classifications, but in layman's terms, we're talking about a tiny vessel of gas that really is stable in bulk solution and behaves much like a colloidal particle. Its size range, you'll see in the literature, a lot of different references to different sizes within Moleaer, and what we principally concentrate on is 80 to 120 nanometers in size. That's very, very small. It's about 2,500 times smaller than a grain of salt, and in that spectrum of bacterium and virus. So super, super small. And then what's unique about it, obviously, is that it follows sort of this Brownian motion and is very stable in bulk solution. Some like to make the analogy like what that looks like is like dust in a sunbeam, and you see the way that it floats and follows this random movement. That's kind of what we're seeing these nanobubbles do in bulk phase and in liquids. So the properties are relatively well understood. We're in the capacity of this webinar, and as it applied in irrigation, we're much more focused on the behaviors. And the three that stand out as being the most prominent and influential in the role of irrigation and changing the sort of the water potential of that water is this electrochemically active surface. Typically a nanobubble has a negative charge. Depending on the constituents in that water, it is possible to change that charge, but for intensive purposes of this conversation, we'll talk about this negative charge and its role in relaxing these hydrogen bonds in the water and consequently reducing surface tension. When you reduce the surface tension, we're also changing the sort of contact angle and the collective influence of those behaviors and how that affects the capillary action of the water is really what we're going to sort of focus on today. So independent validation is key. I mean, we think about, we're talking about something that you can't actually visually see with the naked eye. It's hard to understand what it can mean when you're looking at a glass of water and it looks identical to something that has no nanobubbles. So we do take a lot of pride in working with various types of independent institutions, both academic and commercial, and then as well, I would tell you, certainly over the last 5 years, the sheer amount of literature and papers and peer-reviewed papers that have come out looking at both the fundamentals of nanobubbles and these various different applied studies, even specifically within irrigation and agriculture, it's profound. It's significant how dense that body of work has increased over the last few years. So by all means, there's a lot of reading, there's a lot of independent validation that you can go into. But as it relates for today, pathogen and biofilm control, we've done a number of studies looking at that. Specifically, most commonly in hydroponics, we're looking at Pythium and Fusarium, sometimes Phytophthora. We've looked at how the nanobubbles disrupt biological matrices. We've looked at ROS production through certain sort of complementary or synergistic behaviors with the nanobubbles. And then input efficiency, again, looking at the role of nanobubbles and how they might influence nutrient uptake. We've done a variety of studies looking at tissue samples, soil and substrate samples, as well as soil infiltration. The advantage that we have in today's environment is that we have a lot of technology that we can use. So we're a proponent of using all kinds of different sensors to track these behaviors in real time. And that's critical to understanding sort of the influence from an applied side, and to sort of at least understand and put a little bit of science and understand the modes of action of what's going on. We get a lot of questions about nanobubble generation methods, and to be super clear, there's a number of different ways that you can produce nanobubbles. There are new methods that sort of are entering the marketplace. Every one has its unique advantages and disadvantages, and to share a little bit about our own sort of thoughts on it, we have to start with the applied side. So we have to understand the environment in which we're putting the technology into. We have to understand the constraints of the process. In some cases, energy is a big factor in how one might choose to introduce nanobubbles, but also longevity in the field, durability, sustained production over the course of time. And that's super important to think about when you're looking at applying a nanobubble into a process. Are you choosing the right solution for that? And so our methodology, the one that sort of we've gravitated towards over the last few years and commercialized around, is one that is based on shear. It allows us the least amount of energy input, but gives us the most durability in these sort of extreme environments, and also the sort of scalability factor. So looking at being able to treat very small volumes of water in batches all the way up to several thousand gallons per minute in that. And that's where, in the preference for adopting or commercializing or choosing these different applications in your own process, just think through some of these things quite methodically. Again, there's a lot of information out there, and sort of you see these lasers used as a sort of proxy measurement. It is useful under the right conditions, and what I mean by that is certainly when it's in a laboratory and you have a control and you can do this comparison. It is a very neat, very easy, low-cost way that you can observe and create this refraction of particles in solution. That is not going to differentiate between other suspended colloidal particles or other dissolved salts that may be in solution. So again, just be very cognizant of when you're looking at something like this. These examples here that we're showing are using deionized water. It is in a controlled process. And so just understand the context in which you're looking at these kind of images. And yeah, but if you don't have something like a nanosite, this is a good methodology to use under the right conditions. So yeah, as everybody might gather, Malvern is our preferred way. We have several of their instruments. We've used them extensively over the last few years. Frankly speaking, there's just no way that we could have sort of enhanced our own methodology, not only in sort of the production, but also understanding the applied side. So we've relied extensively on Malvern, and for our needs, it's been the most consistent way that we can sort of characterize the nanobubbles and the methods that we do. And again, the quality of that data has been instrumental in our own learnings. It's over to you, Ragy.
Thank you, Warren. And so I just want to take a moment and talk about how these techniques that are crucial for nanobubble characterization actually work. And I'll start off with nanosite. Nanosite is the product range. Nanoparticle tracking analysis is the technique. So sometimes you hear those two different terms interchanged. And so when we talk about nanosite, what we're doing is we're looking at a number of parameters. One is we can look at particles anywhere from 10 to 40 nanometers on the low end, depending on the density and the scattering efficiency of those particles. 10 nanometers tends to be a little bit more of your metals and metal oxides that might be present. Nanobubbles might go down to about 30 or 40 nanometers, depending on what kind of gas or air is loaded in. And then the upper range has to do with anything that's going to retard the Brownian motion. So the upper limit could be about 2,000 nanometers or so. Anything that's going to, be too slow for analysis might dictate the upper limit. But the beauty of nanosite is that we're looking at particle by particle interactions, and so we can actually give you concentration, and that can be anywhere from 10 to the 6th particles per mil to up to the 10 to the 10th particles per mil. And you can also look at high resolution analysis. So this is particle by particle analysis, where you can look at very polydispersed samples or monodispersed samples. And you can actually gate and determine what is the percentage of your particles that are within a certain subrange and the concentration of that subrange. So that's all available within the software. And furthermore, if you are looking at particles of the same size but of different compositions, one could be something like a metal and then another could be a nanobubble. They might have relative light intensity differences. And so you can distinguish those with the nanosite software as well. And then furthermore, people also will look at, fluorescent moieties in conjunction with nanobubbles. So they'll use any number of our laser modules that we offer to couple with a corresponding long pass filter and look at fluorescently labeled particles and looking at their size, distribution, and their concentration, and comparing that to the total population in the sample. And so the premise behind nanosite is that we actually will record a video of the particles moving around in Brownian motion. And when we're talking about the particles moving, we're actually looking at the light scattered off those particles move in Brownian motion. So we'll record a video and then we'll process that video. So you can see here in the second panel, the random walk of the Brownian motion of each individual particle that's being analyzed. And so you can see that on a frame by frame basis and note their diffusion coefficient and relate that to the size. And we'll talk about that here in a second. And so the final panel shows you that we'll actually give you the concentration versus size analysis and other types of metrics along on the y-axis in comparison to size. And so, again, to reiterate, what we're doing is we're visualizing the light scattered off particles moving around in Brownian motion. It's not like SEM or TEM where you're looking at directly at the particle. But because we're looking at light scattered off the particles, we can actually relate that movement to the size. And the whole analysis can take a few minutes, depending on how many repetitions you want to do of a single sample for reproducibility's sake, or how long the videos you want to record. That will all come into play in terms of the analysis time. But all in all, it is just in a matter of a few minutes. And so the premise, again, is that we have this laser module. And here's a diagram where we show you that the laser beam will go through this prism, and then the prism will scatter light into the suspension of particles. And those particles then will scatter photons, and we're actually looking at those photons moving around in Brownian motion with a high sensitivity camera and a 20x objective lens. And with this combination of the camera choice and the lens and the laser module, we give you a very economic and optimal combination to give you the direct measurement for the full size range. And so this is how it will work. And so what we're doing is we're looking at the mean square displacement, MSD, and relating that to the hydrodynamic diameter through this version of the Stokes-Einstein equation, where you can see temperature and viscosity being factors that to account for. And so you'll see in this video that we just showed, we can see that in the random walk of the Brownian, the Brownian motion of each individual particles, you actually see two numbers next to each particle. The top number is the size for that particular particle, and then the bottom number is the number of frames that particle's been tracked. And so the camera will take 25 frames per second, and we only need to see that particle moving around in that 2D field of view for about a fifth of a second. And so you get a lot of concrete information in a very short period of time. And then we can furthermore look at the number of particles per frame and extrapolate to a known third dimension and calculate the concentration on a frame by frame basis. And so when you're recording a video, let's say that's 30 seconds, that translates to about 700 something frames, or that many averages of concentration. So by the time you finish recording a single video of 30 seconds, you get a pretty absolute number average for concentration and in terms of particles per mil. And so you can, again, look at fluorescently labeled particles, and that's just simply a matter of doing the analysis in what we call scatter mode, and then inserting the corresponding long-pass filter that matches your laser source, and doing the fluorescently labeled measurements. And so you'll see here that the filter is being inserted, particles disappear for a moment, and you can now see just fluorescently labeled particles and do all the same analysis, and then do some profile comparisons where you can look at what is the size differences between those that are fluorescently labeled compared to those that are not, or what's the concentration of those fluorescently labeled compared to the total population. And I also want to take a moment to indicate that sometimes in the case of nanobubbles or other types of particles, you have what we call flaring. And so you might see that they're scattering pretty efficiently, and even if you reduce the camera level, reduce the camera level, you still might see some flaring. And so one way to do that is to incorporate what we call a neutral density filter, or what is called a neutral density filter. And so you can see the population on the left without a neutral density filter, where you might see some really small particles, but with the neutral density filter incorporated, you now have a cleaner image, a cleaner video to record the Brownian motion, and you see that the population has been really fine-tuned to what is truly a nanoparticle moving around, as opposed to a particle that's flaring, and seeing the flaring being noted as individual Brownian motion tracks. So let's switch gears for a moment. So we've talked about the benefit of nanosite and how it works and what it can provide. But then let's also talk about the Zetasizer. Now, the Zetasizer, for anyone who's ever heard of our company, will know that the Zetasizer has been well known for many, many years for both dynamic light scattering and electrophoretic light scattering. Dynamic light scattering is the technique we use to measure size. Electrophoretic light scattering is the technique we use to measure zeta potential. And so what I want to do here is actually just focus on electrophoretic light scattering, because this is the technique that pertains most to nanobubble characterization for all the reasons that Warren has discussed and what we've also presented in the previous webinar. So when we talk about electrophoretic light scattering, what we're doing is we're looking at the response of particles moving or undergoing electrophoresis and using that to determine their zeta potential. And so the zeta potential is really a key for the stability of a colloidal system. And so, the higher the absolute value, regardless of the direction of charge, the more stable your sample might be. You can see here on the left where you have a high zeta potential value will indicate a stable dispersion, and then a low zeta potential will indicate some level of aggregation and an unstable dispersion. And so it's further calculated by looking at the electrophoretic mobility of these particles that are moving under an applied electric field. So that equation is calculated by looking at the particle velocity divided by the electric field strength. And so the electric field strength is further a function of the applied voltage and over the distance between the electrodes. And the distance between the electrodes can be set by selecting the appropriate cuvette, which oftentimes for nanobubbles you'll be using the DTS 1070 cuvettes, which is shown here on the right with the electrodes present. And then the particle velocity is determined by the laser Doppler effect, where we're looking at a frequency shift between a reference beam and then the beam going through a sample. And those will produce two different frequencies, and how those frequencies combine will actually give you a delta frequency. And that delta frequency can then further be used to determine the particle velocity by solving this algebraic equation, where we know the delta frequency, we know the laser wavelength, which is a 633 helium neon laser, and we know the scattering angle that's used for zeta potential, which is 13 degrees. So we solve for particle velocity, and we go back and put that into the equation to calculate the electrophoretic mobility. And furthermore, when we talk about zeta potential, sometimes there's this little misconception that it's just the charge directly on a particle. Well, it's not so much the charge directly on a particle, but more so the electrostatic interaction between charges in the slipping plane around a particle with the dispersant. And so when we talk about that relationship between the particle and the dispersant, there are a number of things that can affect the zeta potential, namely the pH, your ionic strength, concentrations of specific anions or cations, or polyelectrolytes. So all of these will have an effect on the zeta potential, and furthermore, the electrostatic interaction between the particle and your dispersant. And when we report the zeta potential, we can look at the fast field reversal, which will give you the average zeta potential value. And in some cases, you'll get the slow field reversal, which will give you the zeta potential distribution. So here you have an example of a sample that is reporting a zeta potential value of minus 33.6 millivolts. And actually, the slow field reversal will actually tease out a minus 23 and a minus 50 millivolt population for zeta potential. So with that, I will return the talk to Warren, and we'll be happy to take any questions either in the speaker section or at the end.
Great info. So back to irrigation and the nanobubble role there. So we've kind of broken it into these four principal pillars, and our approach is essentially, it all begins with water quality. What we do is we're introducing these nanobubbles that in various different forms. I'll give you some examples in a couple of slides, but it could be at the source water, it could be in lime, it could be in a sort of holding tank or what we would call like a day tank. But in any case, it starts with introducing the nanobubbles to improve either the oxygen level in that water, if that's the required application or sort of purpose of the application, but also then obviously reducing things like certain types of bacteria, algae that may be present in the water. And so it begins with really improving the quality of the water that we're putting in through our irrigation system and feeding the plants with. Second to that, we look at sort of biofilm control. Biofilm means two different things, one of which is you've got your irrigation system, you've got filters, you've got your emitters. It could be a drip emitter, it could be a spray emitter. What we're doing is we're using the nanobubbles to improve the hygiene of that irrigation system. And that means preventing biofilm or disrupting biofilm accumulation on the surfaces. It also means preventing scale deposition on those surfaces as well. And that can mean a better filtration efficiency. It could mean a better distribution uniformity of your nozzles if that's required. But also specifically, there's some good research out there that talks about how the nanobubbles can actually change the sort of biofilm inside the soil as well, and sort of the spectrum of bacteria that may exist there, and changing the dominance of certain types to some that may be more beneficial. And that sort of crosses over to how we look at soil health as well. And what we're observing is, again, reducing the surface tension of that water. As a consequence, we're changing the behavior, the capillary action of that water, and improving that infiltration. So we particularly track things like soil compaction, and again, that's sort of the modes of action there could be multifaceted. It could be a lot to do with just improving the way the water penetrates the soil. It could be helping to change the types of bacterial microbacterial activity that's happening in that soil as well. And that helps to flocculate the soil. And then specifically, another important factor that we've been tracking over various installations is the role of these bubbles to help mobilize salinity accumulation. And that could also be tied to just once we reduce that compaction, we get a little bit more infiltration, penetration, and consequently, we get a little bit more mobility with those salts out of the root zone. So that's really a key thing. And then with addressing these three foundations with nanobubbles, obviously at the root level, improving the quality of the soil around the root zone, the rhizosphere, it's a big factor in terms of root development and root health, disease suppression, and consequently the applied side, the vegetative growth, the strength of that plant, and also its resilience in stressful environments, which could be sort of water deprivation. It could be high temperatures, climate change, or whatever you want to call it, these sort of high temperature events that come through, as particularly Europe over the last few years, looking at the plant's ability to have a little bit more buffering in terms of its tolerance to be able to cope with those stress factors. So again, we kind of group this into two different things. Again, the differentiation here is oxygen versus just nanobubbles. A big part of our installation base is using oxygen as a means to improve the dissolved oxygen level in that water as well. And then you have these added benefits of nanobubbles, which I've just described. So again, sort of breaking it into these two different groups, you've got the role of oxygen nanobubbles to improve the water quality, and then obviously related to root health and these biological processes within the plant itself. So breaking it down just super simply, nanobubble generators, different ways. It is a super efficient way that we can put oxygen into water. What's unique about these processes is that we're doing two things. You're dissolving that oxygen into water, and you're also producing these nanobubbles, which is obviously what we're emphasizing here. But again, we see tremendous results with things like algae reduction, turbidity reduction in water. So the sheer cleanliness of that water can have a big impact on the way your behavior of your filters and obviously emitter uniformity as well. So improving the quality of water at its source before you put into your irrigation system there's a big role for oxygen nanobubbles in that capacity, and specifically is also to help mitigate or offset some of the chemical inputs that one would otherwise use to control things like algae and bacteria or pathogens in that water. And then as it relates to improving root health and plant health, oxygen is obviously vital to sort of the plant development. We're looking at improving things like the ATP and enzyme production. And what we see how that translates to is just the efficiency of the way the plant can utilize sort of less resources or those resources or inputs more efficiently, and consequently its robust development. And again, like I was saying, its ability to withstand these different environmental stress factors, and as a consequence, which I'll show you in a few slides later, is its role in plant yield and the quality of the produce that these plants are producing. So coming back to the fundamentals and nanobubbles again, this is where we emphasize some of the best opportunity for additional research and additional focus on the way that nanobubbles can improve water use efficiency. Certainly where you have compromised soils for various different practices, but particularly soil compaction, or people are having to use well water as opposed to surface water, which they typically were used to. Being able to utilize nanobubbles in a way that reduces surface tension. And so we have some pretty good data, and certainly there's additional data out there from other research institutes looking at the sort of the correlation between the concentration of nanobubbles and surface tension reduction. So again, you're looking at the methodology, how can we potentiate the amount of nanobubbles that go into a particular process, whether it's in line or in a reservoir or in a tank. That should be a focus of how you might approach a different application. And then obviously, I think just again, it's sort of the simple analogy is everybody's familiar with surfactants and penetrants, and this is sort of mimicking some of the benefits that you may be able to get in a non-chemical way. And certainly, I think everybody understands surface tension reduction, whether it be with a chemical like a surfactant, the sort of the reducing that contact angle, and its influence on the behavior of that water as it moves through the soil column. Increasing that lateral movement is what we see, again, utilizing soil sensors, particularly stake sensors, which we're very partial to, where we can actually track by the inch or by the centimeter going down through the soil column and actually seeing how this water is changing its behavior. So yeah, so as we sort of move the influence on the behavior of water and the soil health, again, what we do, we use things like penetrometers to track soil compaction. The results are actually fairly dynamic. Within a few weeks, you typically start to see a reduction in soil compaction. And for those that are not familiar, oftentimes it could be agricultural practice, it could be equipment that's on site, it could be just the way that you may have had accumulated certain constituents in the soil that you get these compact zones. So let's just say it's at 20 inches or 12 inches down, you'll get a compaction zone in that soil, and that's really limiting infiltration. And so even though it may limit the infiltration of the water, most importantly, right, like the way that we're distributing nutrients into that root zone is through the water. So the way that if we can improve and flocculate that soil and improve or reduce that soil compaction, you can indirectly improve the distribution of these nutrients in a more uniform way. And what we see as a result of that is we see a better root development, more lateral root development, more feeder, more capillary roots that you can visibly see with the eye when you actually take samples and do this analysis. So this is kind of working a little bit backwards from sort of understanding how we came to think about these different modes of action. And again, we're in an environment now where people can use sensors and can look at this data in real time. It's become a lot more affordable, and so we're a big advocate of this. This is a particular size type of sensor going down to 46 inches. And what we're showing here is we're tracking two principal things. One is moisture content at the different levels. And then the bottom heat map, what you're looking at there is actually the salinity map. And that's looking sort of red, obviously higher concentrations, blue, lowest concentrations. And what we're showing here on the left-hand side is an adjacent field that's irrigated with the same water, same crop, same control parameters in terms of nutrients and water use. And here we have a sensor that's showing, basically you've got a heat map. You can see a little bit of that compaction zone there right around it's hard to tell exactly, but I believe it's around 20 inches, somewhere in that range. And that gray dotted line is when we actually stopped our irrigation. And what you can see on the sort of the nanobubble treated side is not only do you see that more efficient drain down, so you can see that water now not being inhibited by a compaction zone, but you can see it draining very nicely through that soil column. But also, most importantly, is its impact on the mobility of the sodium salts, which we're particularly focused on. And so you see those start to significantly drop out. And again, just to be super clear, what we're trying to do is we're just trying to move those down through the soil column and out of the sort of the denser root zone. And in thinking of that in terms of input efficiency or water use efficiency, what's a normal practice is farmers will then apply something called winter watering, where you may flood the fields to create this sort of high intensity drain down with a specific purpose to try and mobilize the salts that are maybe fixed in that soil. So it's a very, very interesting way that we can look at water use efficiency in a different way. And sort of we really believe that nanobubbles have a critical role here in improving this water use efficiency. Another interesting observation that we can also share is for those that actually know, a little bit of a different substrate than soil. We're talking about cocoa coir, and grows in some cases preferential to cocoa because of its buffering capacity. That's a good and a bad thing. So it provides a little bit more tolerance for misuse or providing the wrong kind of nutrient, not the wrong kind of nutrients, but the dosing. That buffering capacity allows a little bit more tolerance. What we see here is, as a consequence of that buffering capacity, in some cases it can also start to harbor more sodium salinity in there, and that can be a negative thing. And so this is a particularly a berry grower here in Central California, and here we've applied oxygen nanobubbles to their grow. And very interestingly, you start to see the separation between the water content in that substrate as well as the conductivity. And what's most important is what we're most interested in this particular observation from the data is that you start to see this sort of stabilization of this conductivity. So there's almost like it's reaching sort of a buffering saturation point, and that helps maintain the EC in a much more stable manner, as well as this moisture content, which seems to be not fluctuating in the same degree with the starts and stops of the irrigation cycle. So it's pretty interesting. And I would tell you, as a consequence of this, this particular farm had some of the best yields that they've ever had. And again, I mean, these simple foundation elements in terms of water availability, healthier substrate, healthier soil, better root development, better disease resistance or disease suppression in that root zone correlates to just a healthier plant growth. Nanobubbles, this is a very frequent high-level area, an area of high interest. It's one of the best anecdotal observations we got many years ago. Those that had started to introduce nanobubbles into the irrigation system, they were starting to see less backflushing on their filters, better distribution of the emitter uniformity, and as a consequence, you can start to see how these nanobubbles start to scour the surfaces of inside piping systems and very much like a mechanical process, but it's disrupting that biological matrix, causing that bacteria to become more planktonic and then ultimately flushed out of the system. So again, just for the sake of time, I will, looking at the time here, I'm going to speed up a little bit just to try and cover everything that we have here. Again, treating this irrigation, whether it's in a tank, a reservoir, or inline, again, coming back to how we think about different methods of nanobubble production, the way that you can do this in the most cost-effective, efficient, and obviously sustaining way is an important part of how to think about this. So again, we can go through these real nice and efficiently, but what we see is, again, sort of talking about the foundation elements in terms of soil, water quality, root health, and the consequences of those. As a company, we make it a practice. We don't really sell on the promise of yield improvement, although as anybody that's a grower and understands agronomy and plant physiology, the simplicity of addressing these sort of root elements of plant growing will consequently result in better plant growth and consequently better yields. And what we consistently see, irrespective of the crops, which now is probably close to over a dozen which we work with, from berries to avocados, citrus, obviously leafy greens, and various number of those different kinds of specialty crops, we do see this consistency, which is an improvement in disease suppression, so specifically Pythium, Phytophthora, Fusarium. These are very common ones that we track. And to emphasize, there's a common misconception as it relates to nanobubbles and their antimicrobial properties. We're focusing on improving the environment in which the root is growing. And so as a consequence of that, we're really trying to promote the good bacteria. I saw some questions earlier about fungi and other types of bacteria. When we're converting this into a more oxygen-rich environment, when you're eliminating some of that salinity, particularly the sodium salinity, and you're helping to flocculate that soil, you're changing the way the spectrum of the bacteria that in there, and generally it's a more beneficial dominant spectrum. And as a consequence of that, when we look at pathogens, it's about competitive exclusion. It's really about promoting the good stuff and suppressing the bad stuff. And as a result of that, whether it's a combination of all of that, we do see yield improvements as a derivative of these things. We do see a consistent caliber increase in the size or the grade of the fruit. And whether you're looking at things like bricks and other things like that, we also start to see these common denominators as a result of treating these elements. Blueberries, again, we've tracked, again, this is just emphasizing the sort of the different types of cultivation, whether it be in soil, in substrate, in cocoa, or peat. Again, we see these improvements in soil compaction, better yield improvement, and caliber size. Next slide. Tree fruits, the same, consistently size increase. In the case of citrus, we have seen improvement in citrus and grapes. You see the advancement in maturation, so the ripening of the fruit, the consistency of the color grading, as well as the maturation of size. You can have this opportunity for potentially earlier harvest as well. Next slide, please. Leafy greens, again, we really started our business focused on hydroponics and improving oxygen availability in these sort of submerged systems like deep water culture. We have a vast installation base covering things like deep water culture, vertical grow systems, NFT, and again, there's some specificity of matching the objectives of the grower based on their environment, based on the oxygen levels that they may require, the disease pressure, environmental pressures that they may have. And again, it's not a one size fits all for everybody. There is a little bit of nuance to the way that you might approach different projects. So yeah, nonetheless, again, nanobubbles play an important role in sustaining a healthy environment for these leafy greens. Next slide, please. Peppers as well. We have some examples where it's an organic grower, and they're using organic nutrients, and there's an emphasis on nanobubbles to helping with your nitrification, so conversion of your ammonias or mineralization of your nitrogen into bioavailable form. Oxygen nanobubbles can play an important role in promoting that, either in the nutrient source itself, or even in the plant in the root zone itself as well. Reservoirs as well is another part of our business is really about treating algae in all kinds of different water bodies, and nanobubbles playing a central role to that. In many cases, it's just simply air nanobubbles, and we apply those same learnings, that same application to irrigation reservoirs where water is stored, and it could be supporting anything from berries in a field to greenhouses or nurseries. Really, it's about providing a non-chemical method to support essentially the health, the cleanliness of that water in its source while it's waiting to be used. And yeah, just to conclude, again, it's not a magic bullet. Nanobubbles are really, you should think about as a very complementary, synergistic way that you can work with various different inputs in a way that makes the overall process more efficient. And that's the way that we try and introduce nanobubbles to sort of enhance these different cultivation methods. Our goal is to be more efficient. And obviously with efficiency, with the improvement and reduction in input cost, we're really trying to simultaneously improve the productivity of these processes. And hopefully through these examples here, one can see and understand the potential of nanobubbles in sort of delivering these certain objectives. I appreciate everybody's time, and thanks for listening. Again, obviously, this will be available for everybody on demand, but Moleaer.com has a great resource for additional, whether it's handout, ebooks on various different parts of cultivation, oxygenation, hydroponics. We have a number of case studies as well, which you can pull from the website. Those of you that are interested in specific papers, we can certainly provide reference links to where one might be able to find that. So again, we encourage people to read. The research is out there. As I said, it's certainly accumulated significantly over the last few years. So there's a lot of supporting literature based on all the things that we've discussed today.
Thank you, Warren. And just to, along that line, we have a number of resources available from Malvern Panalytical. We have our main Knowledge Center tab on our main website. We also have these hyperlinks where you can read more about nano-sized, how nano-sized works, and the characterization of nanobubbles. And then whether it's this white paper or the application note on nanobubble applications and characterization by nanoparticle tracking analysis. We also have our Zeta sizer product line that people can read more about. And then we also have our blog site. Our blogs are available at materials-talks.com. That is a Malvern Panalytical website. And there's a blog specifically on bubbles and fine bubbles and nanobubbles. And then we have links that we'll share here with you where you can, if you're interested in equipment and instrumentation for your lab or for your facility, we can get you a quote, a demonstration where we travel with the instruments to your site, spend a day with you, do some characterization to validate the use of that equipment for your research. So you can request a demo or just contact our sales department for any questions you might have. I also want to take a moment and mention that we do have, there is a ISO committee, TC281. It is 10 years old. There's been 18 published standards on fine bubble technology. 14 standards are currently under development. And there's a lot of guidance on the generation and usage of fine and ultrafine nanobubbles, including a number of material, points in the material. So that's available. Malvern Panalytical actually is on that committee, and one of our colleagues actually chairs that committee. So please feel free to look more into that. And with that, I want to also mention that as Warren mentioned, this is a series of webinars. We finished one in December. Then you have today's, which will the recording will be provided at a later point. But then we have two other webinars we are doing together, one on surface water on April 12th, and then another one on wastewater, which is going to be in June, but I think the date has to still be determined. So with that, I will leave you with our contact information. We will send you a lot of information regarding the material you've seen here today, and welcome any questions you might have. And thank you for your time. And thank you, Warren, for your time.
Yeah, that's Ragy. Thank you, everybody.
All right, great job, gentlemen. There are many questions pouring in, more than 40. So we're going to see how many we can get to right now. So I'm going to ask, what is the concentration of bubbles, particles per volume that you're able to reach, Warren?
So concentration is relative to two principal things. So one is the constituents in the water can significantly change the concentration accumulation that one can achieve. Also the methodology. So if we're recirculating, like for example, typical irrigation water, achieving hundreds of millions of bubbles per milliliter is a common metric that we work towards.
All right, and is the generator creating both microbubbles and nanobubbles?
Yeah, so it highly depends on the application. So in most cases, you will always produce a spectrum of bubbles depending on how we want to do it and depending on energy. So if we're trying to minimize the energy use, you will typically produce micro and nanobubbles, yes.
Okay. Ragy, is the nanosite fluorescence option relevant to nanobubble measurement?
It can be. We actually have a customer that got a fully loaded system to look at naturally fluorescent moieties or biological material in the water in addition to their nanobubble characterization. So it just depends on what else is around with your nanobubbles that you want to tease out, and you can tease that out by fluorescence, and you can choose any of our laser modules with the corresponding fluorescence filter, depending on what the material might be. So because of the unknown, this particular customer actually ended up getting all 4 laser modules with all the filters, just to be able to accommodate whatever might be in the water.
Okay, and also Ragy, what is the maximum salinity for measuring Zeta potential and nanosite microscope?
Right now, our current family of systems is reported to have 250 millisiemens per centimeter. Is the highest salinity you can handle while making a reliable Zeta potential measurement. You can read more on the specs of our equipment at our website. If you go to the Zeta-sizer product range. Yeah.
Okay, and Ragy, also, can we use Zeta potential and nanosite for a non-aqueous system?
Yes, you can. So there is a way to incorporate an O-ring metal top plate, that handles both aqueous and organic-based solvents for nanosite analysis. And then for the Zeta-sizer, you can also use not only our polystyrene-based cuvettes for aqueous-based measurements, but you can use our glass or quartz cuvettes for organic solvent-based measurements.
Okay, Warren, how long do nanobubbles typically survive in water? Would they last in a water tank for several days before being pumped out? Are they sensitive to shipping by truck?
Good question. No, so nanobubbles are pretty stable. So we've observed nanobubbles stable for months at a time. There's literature that have looked at nanobubbles being stable for much longer than that. But again, it depends on sort of the agitation that may be inside that tank. But if that tanker was just sitting parked, we would expect a very, very high sort of resilience over a few days.
What is the effect of nanobubble concentration in agriculture?
What is the effect of nanobubble concentration in agriculture? So for us, it means different things, but I would tell you specifically concentration as it relates to biofilm removal and surface tension reduction. Concentration definitely matters. And so sort of the higher the concentration that we can achieve, the lower the surface tension may be as a result. And then also in terms of biofilm removal, certainly the higher the concentration, the more surface area, the more scouring that you are going to be able to achieve with those nanobubbles. So yeah, concentrate more, the higher the concentration, the better.
Okay. Are nanobubbles as beneficial for a hand watering application?
Sure. Yeah. No issue.
All right. Maybe this is for Ragy. Please explain in more details on the Zeta potential distribution. How can we use it as evidence of nanobubble existence in the solution?
Well, so, nanobubbles, like anything else that's forming a particle, will actually have, some colloidal stability to it. And so Zeta potential will actually determine that level of colloidal stability. If you have a low Zeta potential, whether it's negative or positive, that means that particle, whether it's a nanobubble or not, is actually tending to aggregate and crash out of your solution. If you have something that's really, colloidally stable, then, you have this, electrostatic repulsion or even steric repulsion in some cases that will yield a higher Zeta potential, especially for electrostatic, will yield a higher Zeta potential analysis. So.
Okay. Warren, would you recommend aerating your foliar solution, a spray solution with nanobubbles to improve wettability?
Yeah, absolutely.
Is there any correlation between type of gas for nanobubbles and surface tension?
Well, because you have to think about the gas being on the core of the nanobubble, and so it depends on what else is around the nanobubble that would dictate the surface tension, I believe. Maybe Warren has a little more experience. We'll do that.
Yeah, we can check with our R&D guys, but I'm not sure if we specifically looked at surface tension with different gases, because predominantly for us, oxygen and air provide a relatively similar surface tension reduction. The only other alternative I could think of that would be useful in an irrigation environment would be probably CO2 if you're doing pH adjustment. But I don't think we've ever done surface tension reduction evaluation with CO2.
Okay.
I think the more effects, come from the size of the nanobubbles, just like what Warren talked.
And the Zeta potential for sure.
Yeah.
All right. Are there any studies or information available on health impacts to humans in drinking nano-oxygenated water?
Yeah. I would point to Japan. I think, I think there are beverages out there, and there is some limited research on nanobubbles as a drink. It's not something that Moleaer focuses on, but certainly I think there are some studies done on the impact on health. There's actually a really interesting one on drinking nanobubble, oxygen nanobubble, either oxygen nanobubble or hydrogen nanobubble drinking water for poultry. That's pretty interesting. That shows some pretty significant improvements in health and growth. But yeah, it's not something that we're involved with.
Okay. For the soil column slide, how much time was required to see the improved drainage benefit from the field measurements?
We started to see improvements after about 2 weeks.
So maybe we can wrap it up and we can answer more of these questions offline. So, all right, I want to thank everybody for joining us today. Gentlemen, any final words?
For me, I appreciate your time, Catherine, in helping putting this together, and obviously thank everybody for participating, and let's go Nanobubbles. Spread the word, spread the love.
That's the motto right there. Yeah, and I just want to reiterate the gratitude towards Catherine and Edgar for and Jen from Moleaer for coordinating all of this. We really appreciate the collaboration to put these webinars together. I believe it's going to be the benefit for many for Moleaer and for Malvern Panalytical, and ultimately for the customers out there. So Thank you so much for your time.
Big Edgar, I omitted you, but a big thank you, obviously. Thank you for hosting and putting this together.
Great. All right. Thanks, everyone, and have a great day. Bye-bye.
Good one. Bye.